All right, this time. This is gonna be another one of these ones where I'm not gonna talk a lot. I'm just gonna do what I want to do. All right, so it's early Transcendentals, and I'm just gonna be working through a bunch of problems. I think. What I want to know is x is equal to f of square root x. Okay, but then if we have right. Okay, so yeah, it's right. That's a good problem. That's wrong. Uh, this is 0. This is false. Oh, I don't remember this rule. Okay, so if you have like y to the x for some y, then uh it's log, which is really ln. ln y times y to the x. Oh wait, maybe we could do this on paper. Hold on. Oh, I never plugged it in. Hold on. Okay, wait. So let's try to derive this. So the definition, we're gonna have limit is h goes to 0, f of x plus h minus f of x over h. So in our case, f of x is equal to 10 to the x. So 10 to the x plus h minus 10 to the x over h. We're going to get 10 to the x, 10 to the h, 10 to the x. So then we can factor that out. So we can get 10 to the 10 to the x times 10 to the h minus 1 all over h. How do they derive this? Is what I'm trying to figure out. How do they derive this? Well, this goes to 0, then this is going to be 1, this is going to be 0. That doesn't really work. Let me ask. Okay, so wait, they're saying y to the x is actually equal to e to the ln y to the x, which is equal to e to the x ln y, which okay, so that's the rule. First off, I don't know why this is true. This is just a constant, right? Because we're holding y fixed. So then this is going to be and then you can rewrite this back into y to the x is equal to ln y e y to the x. Right, so that sort of makes sense, but okay, so this okay, so just start by taking ln y to the x into x ln y. If you take the x of both sides, so x, then we're going to get e to the ln y to the x becomes y to the x is equal to huh. I never That's wild. Wow. Okay. Yeah, I mean, I'm convinced. All right. Let's just keep moving on. So wait, so wait, let me actually let's do this for real. Okay, so this is chapter This is chapter 3, early Transcendentals review. Okay, so problem 1. This is... Oh. They restart the numbering? That's kind of stupid. Alright, fine. State each differentiation rule both in symbols and in words. How do you derive the product rule? Right. Okay. The derivation of this product rule is weird. Okay. So you get... Wait. So you get... Oh yeah, that's so cool. Wow. This is because then you get these subterms that, wow, that's really cool. Okay. I'm gonna write that down. All right. So deriving the product rule. Say we have some expression f of x times g of x, and we want to take d dx of this. So we rewrite this to be limit as h goes to 0, f of x plus h times g of x plus h minus f of x times g of x over h. Then what we do is we turn this into f of x plus h times g of x plus h minus f of x g of x plus h plus f of x g of x plus h minus f of x g of x. And this is all over h, 1 over h. So then we can rewrite this as 1 over h g of x plus h times f of x plus h minus f of x plus f of x times g of x plus h minus g of x. Okay, so then you can see here, though, that we're going to end up with g of x plus h times okay, but the crazy thing about this is that these two are the definition, because you still have this limit as h goes to 0. So in this case, this is for the whole thing, right? This is for the whole thing. So this becomes just g of x. But then this becomes f prime of x plus f of x. Oh, and I guess this was always just f of x. Okay, so there's the derivation of the product rule. That's pretty sweet, actually. The quotient rule. I'll never remember the quotient rule, but we could derive the quotient rule. Okay. Okay, so let's say we have this expression. We could turn this into f of x g inverse of x. Then it becomes a product rule, right? So then you get then you get G inverse of x f prime of x plus, this is going to be minus wait, did I do this right? We could do this, then it becomes I don't know if that's right. That doesn't look right to me. Okay, so we missed a G prime of x in there. But isn't G prime of x just... Oh, I understand, because... Right. because G inverse of x is equal to 1 over G of x. So if you think of inv of G of x, then you're going to get, this is going to be f and this is G, so then you're going to get f prime of G of x times G prime of x. So what's the inv of if inv... Okay, there we go. So that's that. So then inv d dx of inv of G of x is going to be equal to G prime of x over minus G prime of x over G of x squared. Yeah, okay, so we just need the G prime in there. That was the only thing we were missing. Alright, so deriving the quotient rule is actually pretty easy. Let's see what's next. The chain rule. Okay, if our expression is f of G of x, then the limit goes to 0. We have f of G of x plus h minus f of G of x. over h. So there probably is some fancy thing that you do to factor out or something. Because let's just think about where we need to go. Where we need to go is f prime of g of x times g prime of x, which if we were to write it out as a limit, it would be like limit h goes to 0 of, so this term right here would be it would be f of g of x plus h minus f of g of x over h times limit is h goes to 0. I mean, I think it just distributes. I don't really know about that, but I'm pretty sure it does. And then this would just be g of x plus h minus g of x over h. So this is where we want to end up. So we want to go from here to this whole thing, because this is just perturbing the input on x. This is the definition of the derivative. And all right, I want to get a let's look into that, because that's actually really cool. Let's see, derive the chain rule. Yeah, so we got to this part. Now we set delta G equal to G. Okay, fine. Rewrite the difference quotient. What? This step is weird. So you take what we know, what we had, that we got to this point, but then you rewrite it as instead of over h, it's over delta G times delta G over. So yeah, so this is okay. So I get the symbols, I just don't really understand. So this is chill because you can always multiply by 1. Taking limits, yeah, that is going to be G prime. That's true. And then this. Oh, wait. This is going to be trippy as hell. The limit as delta G goes to 0. Wait a minute. Is that real? That's crazy. So then you end up with f of g of x plus h minus f of g of x over g of x plus h minus g of x. This becomes its own thing, right? But then this um so you, okay, so if delta G is equal to just G of x plus h minus G of x, then f of G of x plus h can be rewritten into f of delta G, oh wait, no, f of G of x plus delta G. Okay, so I get this now, and it's all over delta G. That's crazy. I don't think I've ever actually seen the derivation of the chain rule. Maybe I have, but I don't remember it, and it is so cool. Okay, so you end up with f of g of x minus delta g minus f of g of x. All right, not minus, plus delta g over delta g. So if you just rewrote this as h2 or something, this would be equal to f prime of g of x. That's wild. So cool. That was really fun. The power rule is the easiest. Those ones are really easy to derive, and I remember actually doing those, but I don't think I ever actually looked into the derivation of the chain rule. Okay, so the product rule was also really cool, and then the quotient rule. The quotient rule was basically a combination of the chain rule and the product rule, because you rewrite f over g as f times g inverse, and then you just take the chain rule on inv of g of x. So we just walked through that. Okay. Now this is the part of calculus that I really don't like. I don't remember any of this, man. All right, let's just do it. Okay, so a is n times x to the n minus 1. B is e to the x. C is ln a times a to the x. D is 1 over x. Oh, could we do that? Actually, should we walk through that one? All right, let's see if we can do it ourselves, because that one seems kind of fun. Okay, so what we have here is, okay, so we want to derive d dx of ln x. Okay, so we'll remember that ln x equal to y means e to the y equals x. Okay, that's just remembering what the definition of natural log is. So now what we're going to have is this is equivalent to the limit as h goes to 0 of ln x plus h minus ln of x over h. So I'm pretty sure there's a special rule here. So let's say we have ln of x plus z or something is equal to y. Then this means that e to the y equals x plus z. How do you proceed from there? So there's an identity that I don't know, that if you have ln of A minus ln of B is equal to ln of A over B. Let's see if we can figure that one out. So this is going to be, so let's say we have ln A equals C and ln B equals D. Then we have e to the C equals A and e to the D equals B. Then let's say this is equal to, I don't know, F or something. So if we have F is equal to ln A minus ln B, and how do you derive that? Okay, so wait. Let's just say that. If you have, I think that this is, if you have this is equal to e to the ln A times minus, or wait, what? Yeah, no, it's not minus. E to the ln minus ln B. So this is going to be equal to, so this is equal to e to the ln A over e to the ln B. But then this cancels out and this just becomes A over B. So then, and then this becomes e to the C over e to the D. And if you take the log again, so now you take this log, you're going to get, or ln, we'll write ln A over B is equal to, or wait, what am I doing? This just becomes, and C minus D is equal to ln A minus ln B is equal to ln A over B. Pretty cool. Pretty cool. Okay, so this is the rule for the, what is it called, log difference identity, but what we're trying to show is this expression up here, which is proving, so anyways, we have ln of A minus ln of B. So this is going to end up being, so we can bring this back down here. So we're going to have ln of x plus h over x over h. So this is the same expression. We limit as h goes to 0. Well, they just rely on another limit? Wait, that's insane. They just rely on this other limit? That's weird, bruh. Okay, so I got to hear you. You start with this. Oh man, there's so many symbolic tricks here, and it's all about like multiplying by 1. That's so weird. There's so many multiplication by 1 tricks in deriving these rules. I'm curious, what's the history of these rules? Because surely they didn't find them all out at once, right? Whoa, man. That's crazy, dude. I never knew the history of calculus. So they knew the big ones. They knew product rule, quotient rule, and chain rule. Oh, interesting. And then only finally in the 19th century did they actually develop analysis. Wow, very cool. Very cool. What is L'Hopital's rule? I forgot. Isn't that just as you? Wow, that's a crazy rule, man. All right, let's see. Log base a of x. Um. Ooh. Let me think about that. Log base a of x. What is this rule? I guess that it's the natural log of... Oh, it's probably not. It's probably... Okay, wait. The change of base formula... All right, cool. That one's easy. It's cool going through these. All right, this is gonna be fun. Okay, we haven't done a trig one yet. We're definitely gonna do a trig one, bro. Okay, we're gonna derive. All right, let's try to do it on our own for a second, and then see how far that really gets us. Okay, so let's say that we have... All right, maybe there's a reason they did tan first instead of... Oh, wait, actually, no, I'm going this the wrong way. Okay, wait, we're going to do sine first. Okay, y is equal to sine of x d dx. So we're going to have sine of x plus h minus sine of x over h. Now, I think I was trying to do this earlier. So if you have a triangle like this, you have another triangle like this or something like that, then we have like theta 1, then we have like theta 2. If we want to know I don't know. I have no idea how to do that. Okay, the addition formula. That's what I wanted to know. The addition formula is sine of x plus y is equal to sine x cos y plus cos x sine y. But why? Anyways, okay, so that's fine. So then we can probably factor this. Let me get... This goes to 0. So this goes to 0. So this whole thing goes to 0. Sine h, but this limit, why? So maybe we need to actually go back. Computing limits. Maybe we need to go back to chapter 2. Okay, so now that we have this one, I'm going to do it for cos. I also want to derive this, though. The addition formula. It's like, where does all this stuff come from, man? What the hell? Okay, that's chill, man. That's so cool. Oh wait. Yeah. E to the ix times e to the iy. And that's going to be equal to cos x plus I sine x all times cos y times I sine y. Okay. And you multiply out this big ass thing. Cos x cos y. Bro, Euler's identity is insane. Euler's identity is crazy, man. Okay, wait. So we have cos x plus y plus I sine x plus y is equal to Oh. Okay, so this is... Wait, why must you have this? Because the imaginary part. Oh, it's simply because the imaginary part. You get that. Okay, I get it. That's very, very cool. Dude, Euler's identity, I swear. That is the most insane thing. Okay. So we got sine. Well, did we do sine? No, we didn't actually do sine. Let's walk through sine. Okay, so we're going to figure out what the derivative of sine of x is. Okay, so we want to find d dx sine of x. This is going to be equal to the limit as h goes to 0 of sine x plus h minus sine of x over h. So this is going to be equal to 1 over h times, this is going to be sine x cos h plus cos x sine h minus sine of x. Okay? I think what you do is you then do is equal to sine of x, so 1 over h, sine of x times cos h minus 1 plus 1 minus 1 plus cos x sine h. Then what did we have to do? There was a bunch of weird stuff in there, right? What did we have to do before that? They rewrite this as two limits. So then you get this limit and you get this limit. This limit as h goes to 0. Sine x cos h minus 1. Oh, wait. Is it? No. This is sine x times cos h minus 1. Plus limit as h goes to 0 of cos x sine h over h. So the point is that the limit as h goes to 0 of cos h is equal to 1. So then you get 1 minus 1 is equal to 0. So then you get 0 over... Anyways, I forget how to take limits. We really need to go back to chapter 2. We'll do that at some point. So anyways, but this limit goes to 0. Oh wait, this is 1, but then 1 minus 1 is root. So this limit, this goes to 0. But then this limit goes to 1. Or specifically this part of it goes to 1. So you end up with cos x. So then there we go. We derived the thing. All right. Let's see if we can do it. Let's see. Okay, so cos is going to be the same. Tan is going to be interesting. I have no idea what the... Okay, wait. Actually, you know what? I have an idea. Let's see. Okay, so let's just draw a triangle. Okay, so sine is equal of x. Let's call this x. Is equal to b over c. Cos x is equal to a over c, and tan x is equal to b over a. So then tan x is also equal to sine x over cos x, because you have is equal to b over c times the c over a. And these cancel. Okay, so we can do the quotient rule on this. So tan x is equal to sine x cos x inverse. Now I forget the I always forget the quotient rule. We literally just derived the quotient rule, but I still forget it. It's like all right, wait. We have f over g. We're going to have f g inverse. So we're going to have f prime g inverse. Wait. So all right, so if we just take this as a product, right? We're going to get f prime g, or let's call this h. Let's call this h. H plus h prime f. So then now we just need to take h prime. So h prime is going to be equal to minus 1 over g of x squared times g prime of x. So then this gives us the quotient formula, which is f prime of x over, wait. F prime over g plus minus g prime over g squared, which is equal to f prime. Oh wait, we forgot the f here. So this is gonna be f prime g minus f g prime over g squared. I'm pretty sure that this is the rule. So if that's the case, then we got sine over cos. So we're gonna have, so then dx of tan x is equal to cos times cos minus sine minus sine over cos squared. So then you're going to get cos squared minus, or plus sine squared over cos squared. Isn't this always 1? So then aren't you just going to get 1 over cos squared? Is that true? The question is, what is the derivative of tan of x? But we're trying to derive it. We're not trying to just remember it, because I'm never going to memorize any of these identities. So unless I can just, like we could rewrite this as a product with an inv, so then we can just take the chain rule and then rederive, because I never remember even the quotient rule. I'll never memorize the quotient rule. The only thing I'm going to memorize is the definition of a derivative, which is, limit as h goes to 0. That's the only thing that I can really, that's what I just said, bro. We just did it. 1 over cos squared. So anyways, so we did that one. We're going to move on to the next one. Cosecant. I don't even remember the cosecant. Is cosecant just 1 over sine? Let's see. Trig function. I'm pretty sure it's 1 over sine. Right. Okay. So wait, I have an idea. Okay, so now we're doing d dx of cosecant of x, which is equal to 1 over sine of x, which is equal to sine of x inverse. All right, so let's try to use this just doing the chain rule. So if we have inv of sine of x, then this is going to be equal to f prime, so it's going to be minus 1 over sine x squared times cos x. So this is going to be minus cos x over sine squared. Or is sine squared, is that what that means? I always forget what that means. So, bro, your all caps is killing me. All right, so this is going to be, let's just rewrite this out. So minus cos x, let's just leave the minus sign out of it. So cos x is in our triangle up here. Cos is a over c, and then we're going to be multiplying by b. It's b over c, but it's going to be c over b squared is equal to ac squared over cb squared. So this cancels with this, and we get ac over b squared. No, I'm never gonna memorize it. It's too much memorization. Plus this is more just an exercise. Okay, so hold on. Let me think about this. So we have a over b times c over b. So a over b is inv of tan x times, and then c over b, that's going to be cosecant. Did I do it wrong? C over b isn't that cosecant? Oh, and then the minus. Oh, I think I got it right. Yes, but is memorization understanding? Is it? Who knows? All right, let me double check my answer. Minus cotangent. So inv of tan x is cotangent. So this becomes cotangent x times cosec. Okay, cool. Nice. We did it. That was a good one, actually. I like that one. Because these ones are so weird. Trig functions, inverse trig functions are so goofy. I mean, like minus cotangent x times cosecant of x. Does that mean anything to anyone? I like if I were to even ask, what the hell does the plot? What is the plot of this even? I mean, that's a pretty weird looking graph. Let's be real. And it's because sine of x, when it crosses the zeros, 1 over 0 is infinity. So it has all these poles. Right. Right. Where it has its zeros. Wow, cotangent's pretty cool, actually. Tan and cotan are pretty cool. And I mean, we haven't even gotten into the hyperbolic trig functions yet, too. But those are the 6 main ones. All right, let's keep going. So I always forget this. When you have a -1 here, that's just I'm almost positive that that's the case. Like if we do sines, does this even work? I doubt that this works with their parser. Right. See, that's the totally different expression. Yeah, man. I hate that notation. So then that means wait, what? Dude, that is the most crazy. How is it that how is it that this means sine x squared, but this does not mean sine x to the -1? That's terrible, terrible notation. So wait, what is arc sine? Why is it only defined for a small bit? Wait, what is that? What is inverse sine? Oh wait, wait. What? Wait, so no, the inverse sine takes. Oh, okay. I think I get it. It takes a ratio of side lengths as its input, and it returns an angle as its output. That's what that is. All right, maybe we should do these crazy hyperbolic ones. Okay, I'll be right back. So okay, this will be actually kind of fun to really get into what these hyperbolic trig functions are. Wait, hold on. So I'm good at computer science. Plot this graph sine pi. Y. Okay, I'll do that. I'm down to do that. Let's see. Where's my Desmos at? Oh, it's a heart. That's minus x squared. Squared. Wait, hold on. I think it's like this over 2 plus square root. Oh, cool. Nice. That's fun. What a crazy graph, though. Wow. That's pretty sweet, actually. That's crazy. All right. Enough of that. All right. So what the hell is the inverse tan function, really? Or let's just keep moving on. Yeah, from any of the angles trigonometric ratios. Yeah, this guy John Herschel, dude. If I could go back in time, I'd kill this guy. No, I'm just kidding. But that's terrible notation. Really, that's terrible notation. I would rather just see arc. All right, these rules. All right, let's just see. So yeah. Wait, what is it actually called? Arc sine x x. What is the rule? Ah, fuck. I probably do have to memorize that then. All right, wait. Let's look through the. Let's figure out the. Okay, wait. Firstly, I don't care. Thanks, man. I appreciate that. Like and subscribe. All right. All right. So if we have y is equal to arc sine x, then then if we take the sine of both sides of that, then we get sine y is equal to x. Okay, differentiate implicitly with respect to x. Holy cow. Okay, that makes sense. That's not that complicated. I just don't know step 1. Implicit differentiation. What does it say about that? That's actually useful. You need to know that. Let me go get some more water. Whoa, that's really cool, man. The folium of Descartes. Implicitly defines y as several functions on x. The graphs of 3 such functions are shown in figure 3. We say that f is a function defined implicitly by the equation. Oh. Huh. Yeah, see, that's the thing. This is the whole thing about calculus, man. It's like when they teach you calculus, they just tell you to memorize all these tricks. But it's like you really got to understand this stuff. And it's a very powerful tool, implicit differentiation. Instead, we can use the method of implicit differentiation. This consists of differentiating both sides of the equation with respect to x, then solving the resulting equation for y prime. In the examples and exercises of this section, it is always assumed that the given equation determines y implicitly. It's always assumed that the given equation determines y implicitly as a differentiable function of x, so that the method of implicit. Yeah. So okay. So that's just the requirements on the thing. So we have x squared plus y squared is equal to 25. Then we're going to get 2x plus yeah, this is going to be 0, right? Wait, what? Oh, but it's assumed that this is a function of x. Right? So this is going to be this. So you're going to end up with 2x times 2y y prime because this is the chain rule, right? So you actually, yeah, oh, here you go. Yeah, see, I'm not even reading. Okay, that's really cool, actually. Okay. All right, so we can go back here now that I kind of get some of the backstory. So you write, okay, so yeah, so you take this original explicit form of y, but then we convert it into this implicit thing. And then we take the derivative of both sides and we get cos. Okay, so we're going to, okay, wait. The way that I'm going to want to write this is sine of y of x is equal to x. Then you get, so you're going to get f of g of x, right? So you're going to get cos y times dy dx is equal to 1, right? So there we go. So yes, so cos y of x times dy dx. Then you differentiate the right side, you just get 1. So now we're going to get, so what we're going to get is dy dx is equal to 1 over cos y. So what is that? What does that mean? That means that okay, so we get dy dx is equal to 1 over cos y. But we need to rewrite this. We know that y is equal to, wait, what? Finally, sine of y is equal to x. We know that, oh, wow. Okay, so you need to then do a next step. You need to substitute it back in. Okay. Okay. So then you say, cos y is equal to 1 minus sine y squared, which is equal to 1 minus x squared. And then where does the square root come from? Nope. Oh, because we need to take the square root. Yeah. Okay. All right, that makes sense. That's really cool. All right, we'll do another one of those. Ugh. Calculus is cool, man. I didn't appreciate just how cool calculus was in high school, but calculus is actually really cool. All right, so what are we doing now? We're doing y is equal to cos. I'm not writing that. I'm writing arc cos. All right, so let's get on here. All right, so we have just okay. So what we're gonna do is turn this into. We're gonna apply cos, and since and then we're gonna get cos y is equal to x. What we're trying to compute is we want d dx arc cos x. Okay, so what we're gonna do is we're gonna apply d dx to both sides. But what I'm gonna do is I'm gonna write this as cos y of x So then we want to take the derivative of this. So we're going to get minus sine y of x times y prime. And we'll write this as dy dx. And then this is going to be equal to 1. Okay, so then we're going to get dy dx is equal to minus 1 over sine y. Okay, but we know that sine x squared plus sine cos x squared is equal to 1. And we can easily, this one's easy to derive because this one is just, we have our triangle here, A, B, C. So we're going to have B over C squared plus A over C squared. So we're going to get B squared over C squared plus A squared over C squared is equal to B squared plus A squared. And then we can just multiply both sides by C squared. And we get the Pythagorean theorem. We get C squared is equal to A squared plus B squared. So that's easy. So that implies that sine of y is equal to 1 minus the square root of 1 minus cos y squared. And since cos y is equal to x, this is going to be equal to 1 minus x squared to the 1/2. So this is sine y. So then dx of cos y of arc cos x is equal to minus 1 over 1 minus x squared to the 1/2. My lighting is all messed up. That's okay. And we'll just double check it in Wolfram. Cool. All right. This has actually been a really good review, man. I haven't done this stuff in forever. All right, so tan, we should probably do arctan as well. Okay, so let's just think about our triangle, right? So tan of x is equal to b over a in our triangle. This is x. And arctan, and so if we apply arctan to both sides, we're going to get x is equal to arctan of b over a. So we can have, if we have a 45, 45, 90 triangle, then b over a is 1. And so then we should get, arctan of 1 is equal to pi over 4. That's what I would expect. So let's figure that out. So arctan of 1 was pi over 4. Okay. Very nice. So okay, let's figure this out now. Now we can do the math. Okay, so if we have y of x is equal to arctan of x, then we want tan of y is equal to x. The derivative of tan, we're going to have, what was it? It was like f prime g minus g prime f over g squared. I'm pretty sure that that's right. And so then you're going to get, what is it? So it's going to be sine over cos. So this gives us cos squared minus plus sine squared over cos squared. So then you get 1 over cos squared is equal to sec squared. So this is that, right? Okay, so that's d of tan. So we're going to get 1 over, wait, but this is actually not all we have to do because this is of x, right? So then we need, so it's going to be dy dx times 1 over cos squared x is equal to 1. So then we're going to get dy dx is equal to cos squared x. But how the heck are we going to rewrite cos squared x? Or wait. Y. In terms of tan. All right, I need help. I can't figure that out. Wait, what? There's all of these identities, man. What the heck? I took like a 5-minute break or something like that. Okay, time to lock back in. More identities that I don't remember. Okay, so apparently 1 over cos squared x is equal to 1 plus tan squared x. Okay, so let's just figure that out. All right, so if we have, okay, so cos equals a over c. So then we have c squared over a squared is equal to 1 plus b squared over a squared. Oh shit. Damn. Okay. That's pretty crazy. Okay, fine. Fine, bro. Fine. I don't even freaking care. So anyway, so we get this. Where were we though? Wait, what? So we had y prime is equal to okay, so this implies that cos and that's a squared over c squared is equal to 1 over 1 plus b squared over. Okay, so then we get okay. All right, I'm convinced. That's pretty simple. All right, so now that we have that, that means that we can rewrite dy dx equal to 1 over 1 plus tan squared y, which is then 1 over 1 plus x squared. Okay. So this is the derivative of arc tan x. Cool. What's next, bruh? What's next? Oh, I was excited for this one. So what the heck are the hyperbolic trig functions? What is that? What does that even mean? Dude, I never really learned this. Conic sections are so cool. Dude, if I had stumbled on conic sections like 3,000 years ago, I would have thought that that was God, I think. This is the simplest hyperbola? Okay. That's pretty crazy, man. Apollonius of Perga. Dude, ancient Greek, man, how cool would it be to time travel to ancient Greece and just walk around and see people hanging out? That'd be so freaking cool. All right, let's stay focused here. Let's see if these expressions are important. I feel like oh. Uh wait. Hold on a minute, Buster. Okay, so it doesn't flip like sine. Tan H is actually pretty important though. See, that's the thing. Oh, well, a lot of this stuff carries over. That's pretty. Okay, so that's really all we need to remember. I mean, I feel like a lot of, for the purposes of the test, I feel like what I need to remember is that sine H of x is equal to e to the x minus e to the minus x over 2. And then cosh Okay, well, they occur in differential equations, so we definitely gotta know this. Or should we just derive one? We'll do one derivation. Why not? What else are we doing? All right, so we're gonna figure out. So first off, sine h of x is equal to e to the x minus e to the minus x over 2. And we want to compute d dx of sine h of x. Okay, so we're going to do it using the limit, just for shits and giggles. So first off, let's do 1 over h times e to the x plus h. We can actually do this, I think, because, right? We'll just do this. So yeah, we can just take this 2 here, I think. This is going to be minus e to the x plus e to the minus x. Okay. Let's figure that out. So this is going to go to 0, and that's also going to go to 0, right? E to the minus x, as x goes to 0, because then as x goes to 0, this goes to 1. Yeah, so this still goes to 1. So this goes to 0 too. So then Wait, then how the hell do you get the? Because the hyperbolic, because this of x is equal to e to the x plus e to the minus x over 2. So, okay, I don't know how to derive this. I mean, yeah, that's. Actually, you know what? A better question is how to differentiate e to the x. We take. Wait. Oh, but in computing this limit, we can take this e to the x out. All right, so there's some logic like based on a series expand or something. I don't really know that, but the limit equals 1, so then we get e to the x. That's kind of a crazy one. All right, I think we're ready to move on. What is logarithmic differentiation? Dude, x to the x is a sick function. What the hell? It's pretty cool, man. All right, let's figure that out. I've never done that. I don't even remember that. Oh, cool. Okay. So dx of x to the x. First we set y equal to x to the x. Then we take ln on both sides. So then we get ln of y is equal to ln of x to the x, which means is equal to x ln x. Okay, so we have ln y of x is equal to x times ln of x. And we're going to take the derivative now implicitly. So we're going to get f1 over y times dy dx is equal to ln x plus 1 Okay, then you just multiply both sides by y, and you're going to get dy dx is equal to y times ln x plus 1. And then you substitute back in. Okay, so logarithmic differentiation is really just a subset of implicit differentiation. But that was a good problem. All right, so here's a harder one. Whoa. Let's look at that. Wait, what was it? Cos 0 equal to 1, 1 to the 1. Okay. Wait, so how do you do this one? Oh, it's all about bringing the exponent down. So then you get this. And then you get this. Where is it? Okay, there's the product rule expansion, some simplification. Then you. All right, that's pretty sweet, actually. Cool. Okay, are we just gonna spam calculating derivatives? Kind of sucks, but maybe it's worth the practice. Just to get back in the spirit of things, you know? And then we definitely need to do chapter 5 too. All right, let's just take a bunch of derivatives, I guess. Why not? All right. All right, so we're just going to take a bunch of derivatives. What was it again? It was let me actually read through these because I don't know how many of these I need to do. Okay, screw it. Let's just like spam these. I don't know. This gets canceled. This doesn't get canceled. Wait. Oh, but the H cancels there. So then this goes to 0 because H goes to 0, but then this H cancels with this H. Um, pretty neat. All right. Doesn't matter. We don't need to do this. But yeah, you do the binomial expansion. All right, then so the final result is going to be minus 1 over I'm going to double check. Cool. All right, number 3. Okay. What? Oh, you know what it is though? I think it's if you have x 1/4, but this squared, it's not. Yeah, because x to the 1/4. Oh, okay, so this actually cancels. Wait, what? Oh, okay, yeah. So this is actually x. Then this becomes 1. So then, yeah, so you get 2x minus 1 over square root x plus. Where the hell is that minus coming from? Oh, wait, this isn't a minus. Where's the 2 come from? Yeah, and the 2. Okay, cool. That took a while. Holy crap, dude. I'm so bad at derivatives. So we should get 1 over 1 plus cos squared times this is g prime. Damn, I don't know what else I need to do. Tan over 1 plus cos. All right, that's good enough. Dude, number 8 is tough. I don't know how to do number 8. I wonder if they have an answer for that one. That one's crazy, man. Okay, number 9. I'm skipping that one. ln of x. How do we take this derivative? Let's see. All right, that one was easy. I like that one. That one was cool. Yeah. Minus. Why does it matter? All right. Okay. So we should be able to make this. I think this is it. No. What is it? What is it? Uh, it's 13. Okay, hold on. All right, let's see. Minus 1. All right, I think that's right. Yeah, I'm not from India, bro. I just said that. मैं भारत नहीं से हूँ. मैं हिंदी नहीं बोलते हूँ. Okay, ln seek x. So if, let's see, so we get f prime is equal to 1 over x. G prime. What's the derivative of secant? Differential equations, but I'm just doing a review. Okay, what's G prime? Secant's derivative is bro, these trig functions shit. Dude, I don't know the derivative of secant. The derivative of secant. Sec x tan x. Oh yeah, because okay, what we can do is we can just write it as, we can write sec just as 1 over cos x. Then what we can do is we can just say f equals 1, g equals cos. Then we get f prime g minus g prime f over g squared. So we're going to get, so this term goes to 0. So then all we are left with is sine over cos squared, which is going to be, wait, is that true? Oh yeah, so this is going to be equal to sec times tan. All right, you're right. Wow, Tesla's hella fast. What the hell? Okay, so then, all right, so this is equal to sec tan. So then we're going to get f prime g prime for the chain rule on this. So then this is going to be equal to 1 over sec x times g prime, which is sec x tan x. So then this cancels, and all you're left with is tan x. Let's see if that's true. This is problem 14. Okay, cool. Nice. That was easy. 15. Oh man, this is an implicit one. Y plus x cos y is equal to x squared y. Wait, hold on. If I divide by y... Oh, no. What am I talking about? Wait, but if I do... No, wait, I don't know how to do this one. I mean, I know you can just get dy dx plus... Oh, this alone is annoying. Because you're going to do... Because it's going to be x... it's going to be cos y plus x dy dx. Let's see, am I still in... This is just that. Let's see, cos x squared. For this one, you say f equals cos g equals x squared. So then you're going to get, yeah, just f prime. So then this is just, so this is easy. This is just a chain rule. It's not a product rule. So then we're going to get minus sine y. And then that's going to be equal to, and then you have a product rule over here. Dude, these implicit ones are crazy, man. I think this, what I'm learning is that I just need to practice the implicit ones. Okay, 16. I'm not doing 16. That one sounds horrible. Because it's a 16 is a product rule on a quotient rule. Or no, a power rule and a quotient rule. All right, let's do 17. Y is equal to arc tan. Oh, wait. Arc tan x to the 1/2. All right, let's see. What do we have to do here? So f is equal to x. F of x is equal to x to the 1/2, and g is equal to arc tan. So f prime is just the classic 1 over 2 root x, and g is equal to what? What is this one? I don't remember this one. Well, I think a sine is 1 over 1 minus x squared to the 1/2, and a cos is minus 1 over... I think that's correct. So can we just figure this out? Wait, but is a tan equal to a sine over a cos? Is that a thing? I don't know if that's true. Okay, so that's not true at all. So, wait, how are we gonna take the? So I think we have to do. Oh yeah. So the way we have to do this is let's take tan y is equal to x. Dude, I'm so bad at the trig, man. Holy cow. So tan y. What the hell is the derivative of tan y? Or tan x even. Whoa, it's getting so windy. Okay. So the way that they do it is they just do the quotient rule. So if you have sine over cos, then you're gonna get. Oh yeah. I should always remember that. So then it's gonna be f prime g minus g prime f over g squared. So this is gonna be like So this is gonna be like cos squared plus sine right, yeah, over cos squared. So then you get this 1 over cos squared is equal to sec squared. That's right. So then, okay, that's how you do it. All right, so what problem are we on right now? We're on 17. What's up, Hardit? Okay, so for 17, we're doing y is equal to a arc tan the x to the 1/2. So f of x is equal to x to the 1/2. F prime of x equal to 1 over 2 root x. G is of x is equal to a tan x. G prime is equal to oh wait, but we didn't finish that. So we ended up with sec. So we had tan y is equal to x. Then we got dy dt or dx times sec squared y is equal to 1 because we take dx on both sides of this for the implicit differentiation. Then what are we doing here? We're going to divide by sec squared, so we're going to get dy dx is equal to 1 over sec squared, which is just cos squared, right? This is y. Wait, but I think that there's a we just did this, but I always forget. I always have to just draw a triangle. So the idea was that we have sec squared, and we're trying to write it in terms of tan. So we have c squared over a squared is equal to, and I'm pretty sure it was like I think it might be 1 plus and then b squared over a squared. Then you multiply both sides by a squared and you get, yeah, that's right, because then you multiply both sides by a squared and you get c squared is equal to a squared plus b squared, which is correct. So then we take this and we're going to get d is equal to 1 plus tan squared y. Okay, but this is x, so then dy dx is just equal to 1 plus x squared. So I think that dx a tan x is equal to just 1 plus x squared. I think that's true. Let me figure out if that's right. Oh, wait. Is it? Oh, yeah, you're right. Because this is... Yeah, you're right. Because this is 1 over sec squared. So then this has to be 1 over that. So then, yes. Okay. All right, so this is equal to g prime, right? Okay, so now we can just do our chain rule. So we're going to get 1 over 2 a tan x to the 1/2 times g prime, which is 1 over 1 plus x squared. Okay, I think that this is the full derivative. Let me double check. Problem 17. Okay, this is correct. I just double checked it on a calculator. This is correct. Okay, problem 18. Cotangent of cosecant of x. You've got to be kidding me, bro. These trig ones are terrible, man. I'm not enjoying the trig. Okay, so... Alright, so f equals cot, g equals cosecant, f prime... Okay, derivative of cotangent. So, okay, if we just take this as cos over sine with cot, then we can do quotient rule. So we're gonna get minus sine times sine plus minus g prime, that's minus cos times cos. All right, so we're gonna get minus sine squared plus cos squared over sine squared. So this becomes minus 1 over sine squared. So what does that become? That's just 1 over cosecant squared, right? So f prime is equal to cosecant x squared. Then g prime. Okay, these cosecant ones are weird. Oh yeah, you're right. You're right. Okay. So, but g prime, I'm so bad at these. So, oh wait, no, I know what to do. Cosecant x is just equal to 1 over sine x. So we can just do this thing with another quotient rule, but this term goes to 0. So it's just going to be minus cos times sine over sine squared. So this is going to be one of those ones where it's like, so cos over sine is cotangent. So this is going to be minus cotangent times cosecant, right? Cosecant x. So I'm pretty sure that's what it is. Minus cotangent x times cosecant x. So then now we can just plug in for the chain rule on this function. So we're going to get f prime g of x times g prime of x. And that's equal to where's my f prime? So we're going to get minus cosecant cosecant of cosecant x, and this is all squared. I'm pretty sure that's true though. And then times what is this? This is equal to G prime times minus cot x cosecant x. Okay, so we should be able to simplify this a little bit. So it becomes because so the minuses don't get canceled out, and then we get cosecant x. Oh wait, we can't actually. I think this is as simple as it goes because you can't just combine these. All right, let me double check my answer, but I think that I got it. It was 18. Cot times cosecant times cosecant of cosecant squared. All right, cool, we did it. That was correct. Okay, 19. Oh, geez. Okay. 19 is y is equal to tan of 1 or of t over 1 plus t squared. All right, so this is going to be a chain rule with a quotient in the okay. So first off, tan okay, let me just for the muscle memory. So we got sine over cos. We're gonna get okay. So tan dx of tan x is equal to secant squared x. I'm almost positive that's the case because you get this. Yeah. So we just did that. So now I'm starting to memorize these things just by repetition. Okay. So f equals tan. G equals t over 1 plus t squared. And f prime is equal to secant squared g prime. Let's see, t over 1 plus t squared. So we're gonna get f prime g minus g prime f over g squared. So we're gonna get 1 plus t squared minus 2t times t over 1 plus t. Is it t squared? Squared. Okay, that's what I thought. So this is g prime. We can probably simplify this though, right? So we're going to get 1 plus. So, but this is going to be minus. So this is going to be 1 minus t squared over 1 plus t squared squared. Okay, so I think that that's as simple as you can write that. So that's equal to g prime. So now we just have to plug it all together, right? Because we got both of them. So it's just going to be f prime. So it's going to be secant squared t over 1 plus t squared times 1 minus t squared over 1 plus t squared all squared. Okay, I think that that's the answer. Let me double check. Okay, I think it's right. All right, I'm pretty sure that's right. Okay, what are we on? We're on problem 20. y is equal to e to the x secant x. All right, so this is just going to be e to the f of x is equal to f prime e to the f. So, so f prime, we just got to compute f prime. So x sec x equals f. F prime is equal to sec x plus x times, okay, so then secant is 1 over cos. So we're going to get f prime g prime, g prime. So then we're going to do, this goes away. Then we're going to get just minus g prime, which is minus sine over cos squared is going to be equal to minus tan sec. Is that right? So this becomes a minus x tan x sec x. So then we're going to get, so it's just going to be, yeah, so it's going to be sec x minus tan x, oh wait, x tan x sec x times e to this x sec x. Is that it? Oh, wait. Somehow this minus I messed up. Oh, because this becomes, yeah, okay. And this goes away, so then this goes to a plus. Okay. So that's thank you. All right, so that's that one. 21. Motherfucking 21. Oh, geez. Okay, this is a good one. Y is equal to 3 to the x ln x. All right, so we're going to get, oh, geez. I'm pretty sure that a to the x is equal to, I forget. Oh, God, I forgot. Damn, I forgot this one. I mean, I know that we could probably do, like, an ln x to the x thing here, but, like, the real question is how do we change this to an e to the, because what we want to get is we want to get, like something like ln 3 e to the ln x to the x, and then we can cross this, and then we get just like ln 3 x to the x. But I don't know if that's, I don't think that's right, because then if you have this, oh, this one actually has an interesting derivative, x to the x. You have to do, I think you do this. I think for x to the x, you go y is equal to x to the x. Then you take the natural log. So then you get ln y is equal to ln x to the x is equal to ln y is equal to x ln, but then you take dy or d dx, and you get 1 over y times dy dx is equal to ln x plus 1. And yeah, that's right. And then you get dy dx is equal to y times ln x plus 1. But y is equal to x to the x. So then you get x to the x times ln x plus 1. So this is d dx of x to the x. Okay, but now that we have that, we still need to figure out what the hell this change of base thing is about. Because it looks like that's how you're supposed to do it, but I don't know. Oh, okay. So all right, so the rule is d dx of a to the u of x is equal to a to the u of x times ln of a times u prime of x. So u prime is, so we still needed to do this, but we were missing out on it. So what we wanted was, so we wanted 3 to the what is our, x ln x times ln of 3 times x to the x times ln x plus 1. It's getting too windy out here. I'm gonna have to go inside soon. Having a really good session. E to the ln, just do e to the ln 3 times. Can you do that? Let me see if that gives the same. Does that give the same thing? What's up? Wait, hold on. Let me see if that's right though. 3 to the x ln x times ln 3 times ln x plus 1. It doesn't have this in here though. But u prime. Oh, you know why though? Wait, you know why? Because if you have x ln x, you're gonna get x over x plus ln x is equal to, okay, so this is not, I don't know what I was doing here. This is like, I think that this is it's if I didn't have the log there. I think that that's what I was thinking. Yeah. Okay, so I didn't. That was sort of a waste of time, dude. It didn't go well. But I just didn't have the. Yeah. Because the thing is, I'm taking differential equations right now, and this teacher, bro, he's one of those guys that, like, the homeworks he gives, like 2 homework problems, and they're like easy. They're like so easy, and then the test comes around, and you're like, bro, what are you talking about? So I just gotta like, cause it's been like a long time since I've done calc. So I'm just reviewing, bro. Because like, there's some gaps in my knowledge because you never use this stuff, right? So I mean, all these rules they rarely come up. So, anyways, I'm just doing some practice. And then the integration practice is going to come soon too, because I just don't know what the hell is going to be on this next quiz. This first quiz caught me so off guard. Oh my god, it was brutal. I don't know why these professors are like this. Like, give homework that's reflective of what the test is going to be like. Don't just like dick around on the homework. Exactly, dude. It's like these guys are such. I don't know. It's really the worst because it's like you're not a good teacher by doing that. You're not like showing us, oh, the real world's hard. No, you're just saying like there's no way to prepare for this exam because you have no idea what the hell is going to be on it. Such bullshit. Wait, so is it the case that 3 to the ln or 3 to the x ln x is equal to e to the ln 3 x ln x? Is that true? Let me ask Chat GPT. You been seeing me whiling on Twitter? Wait, what have I done on Twitter? I don't think I said anything crazy on Twitter. I think I I think I just said that thing about my Series A. I said I raised a Series A. Or in general. Oh, okay, so yeah, we could just do that. That's way better. Okay, so yeah, so we can just do this. No, no, I was just fucking around. It's here, I'll type it in. I wait, it might have an E on the end. Waffle? I forget. Well, tell me so I can tell me so I can delete some of it. Cuz I need to delete the like sus parts of that. All right, wait. I'll be right back in like 1 second. Okay. I'm back. Let me see. Maybe it's deleted. Yeah, you probably. I actually remember what it was. It was about Santa Claus, and I did delete that. I remember that. I remember reading that like a day later, and I was like, "This can't. This does. This is not right." Okay. Um. Yeah, I remember that one. No, most everything. Yeah, okay. All right. 23. Wait, no, 22. secant of 1 plus x squared. F is equal to sec. G is equal to 1 plus x squared. F prime is equal to 1. It's going to be 1 over cos. Then we're going to get minus. Then we're going to get 2 minuses, right? So we're going to get a sine squared. Wait. It's going to be F prime G. Wait, is this in frame? Chord spicer? No. What is that? Sad cosig. All right. Minus prime F. So G prime is. Oh, so this is going to be minus sine. No, it's going to be sine over cos squared is equal to tan sec. Oh, yeah, tan sec. Okay, F prime is tan sec. G prime is equal to 2x. So then this is going to be a pretty easy one. It's a niche community. All right, so wait, actually, how's this going to go? Because this is going to be, I think this is going to be tan G sec G times 2x. Because it's going to be F prime G of x G prime. So this is going to be equal to tan of 1 plus x squared times sec of 1 plus x squared times 2x. I think that's right. Let me double check. This is 22. 2x sec 1 plus x squared tan x. Okay, cool. That was easy. That one was really easy. Okay. 23. Y is equal to 1 minus 1 over x to the minus 1. Oh, fuck. There's got to be a way to do this better. I mean, if you have a 1 over 1 minus 1 over x squared, or just x. I hate ones like this. I always get so confused. Maybe I could just do a power rule thing. Just do like my... So if f is equal to inv and g is equal to 1 minus 1 over x, f prime is equal to 1 over minus 1 over x squared, right? And then g prime is equal to, it's going to be 0 minus, this is going to be minus x to the minus 1, which is going to be equal to 1 over x squared, right? So this is going to be 1 over x squared. Am I tripping? I think that might be right. So then we just need to take f prime. So this is going to be minus 1 over 1 minus 1 over x squared times g prime, which is 1 over x squared. Yeah, the chain rule is the best way to do that. All right, let me double check though. Yeah, that's right. Okay, that one was actually easy. Okay, which one is next? 24. Oh, this one looks brutal. Oh my god. Okay, 24. Y is equal to 1 over x plus square root x to the 1/3. Okay, this won't be so bad because we just do the quotient rule, right? So g is equal to x plus root x to the 1 to the cube root. So then f equal to 1 f prime g minus g prime f over g squared. Well, all we got to do is this goes to 0, and we just got to figure out what g prime is. G prime, uh, so we're going to just have, so g is equal to x plus root x to the 1/3. So then we're going to say h is x plus root x, or yeah, and I is equal to x to the 1/3. So it's going to be, wait, 1/3 times, so this is going to be g, or it's going to be, wait, why did I name it like this? This is f, and this is going to be g1. So it's going to be f prime g, g prime. So hold on. So prime is equal to 1 plus 1 over 2 root x. And f prime is equal to, what's it going to be? Why am I blanking out on this? It's going to be a 1/3 times x to the 1/3 minus 1, which is minus 2/3. So is it not just going to be 1 over 3x to the 2/3? I think that this is, so this is f prime. So now we can just do the chain rule. We're going to get 1 over 3 times g, which is x plus root x to the 2/3 times g prime, which is just 1 plus 1 over 2 root x. Okay, so that's, wait, really? Oh my god, dude. These are so nasty. I hate when you get all these crazy exponents. So then, anyways, you do the quotient rule. Show that a function f satisfies. Dude, I haven't done an epsilon delta proof or whatever in forever. It's been a while, man. I have been wanting to work through my real analysis book a little bit more, but I'm reading this amazing book by Michael Sipser on the theory of computation. And if I have any free time, I want to work on that book because that book is crazy. Regular languages, computational complexity. It's got all the freaking cool stuff in it. All right, and I'm pretty sure you just take this and you do the quotient rule or something. What a nasty one. I didn't like that one at all. Wait, hold on. What time is it? Okay. I gotta go soon. 25. Sine. Oh, this one. I hate these ones. No, I never. I don't know how to do these. It's all the implicit differentiation ones I don't know how to do. All right, I'm going to end it. I feel like that was pretty good. There's probably a whole bunch of other stuff in here. These. A lot of good problems in here. Calculus is actually deeper than I remember. But yeah, I mean, the real thing is I got to get to these review things because does this have, oh, you see, we got to go through chapter 5, 6, and 7. All right. So I need like 3 more solid 4 hour review sessions on just integration. All right. So peace out. If you guys are still here, I'll see you.